Now we will move to the next topic here, which is expectation and variance of continuous random variables. You can see that we are using the same terminology, which is you will see the relation to discrete random variables. In fact, it is the same definition, just that in all places where you had summation, they will be replaced by integration. That is the only difference. What is the let us say you have a continuous random variable x, which is from omega to reals. What is the expectation with density fx? What is the expectation of this random variable? The formal definition is that it is integral minus infinity to infinity x into fx of x dx. Here you can see the similarity to the probability mass function, which is a discrete random variable analog, where you had sum over x into fx of x dx. So, here you have integral minus infinity to infinity x into fx of x dx. Right. The only difference is that you have a dx here and an integration which you had just which replaces the summation for the discrete random variable case. The physical meaning remains the same, where in the case of discrete random variables I asked you to imagine the probability mass function as a literal mass on a scale, and the center the point at which you can balance the scale is the expectation, and in an exact manner exactly analogous way you can define let us say you have the probability density function of this some random variable, let us say it is like this. You can have a density function which looks like this curve, and the point you can imagine this as a scale where the mass of the scale at that particular length is proportional to the height of the curve. You can imagine a scale like that, and the point at which you can balance that scale is exactly equal to the expected value of x. So, the center of mass for a discrete set of objects corresponds to expectation in the case of discrete random variables, but a center of mass of sorts for continuous objects that corresponds to expectation for continuous random variables. So, that is expectation. You can we will see some examples of expectation, how we will compute expectation for some simple examples. Right. Let us take the simplest okay. But before we do that, let us see some properties of expectation. Right. So, some of the basic properties of expectation are as follows. Let us do the properties. The first property is that linearity of expectation, that is you have two random variables x and y, expected value of x plus y is equal to Ex plus Ey. You have two random variables x and y. This is one of the most basic properties of expectation. X and y can be any two random variables, of course they must be from the same experiment. You can't have two different experiments and compare random variables, they have to be the same experiment, but they can be the same random variable, they can be completely independent, they can be however the case may be. Its linearity of expectation is one of the most basic properties of expectation. I am not going to define with it is pretty easy to prove this, but I am not going to prove that anyway. Then there is the other property which is let us have let us say y is equal to some function of the random variable x. See, if y is equal to g of x, what is the expected value of y? Of course, you could compute the probability density function of y, and then you could apply this from first principles you can compute the expectation of y. But there is a much easier expression which is analogous to the discrete random variable case. Ey is simply equal to integral minus infinity to infinity g of x into fx of x dx. You can see this is much simpler because I have not computed the density function of y at all. I have just used the density function of x, but instead of multiplying by x I am multiplying by g of x. What is the logic behind this? It is a pretty intuitive logic, it is pretty easy to see for discrete random variables. A very similar logic works for continuous random variables also, but I am not going to prove that, right. For discrete random variables you can recall the logic, you can go back and check the logic if you want, but for continuous random variables it is exactly the same logic where you do not need to compute the density function of y. If you have the density function of x and y is g of x, to compute expectation of y you can just have integral over minus infinity to infinity g of x into fx of x dx. So, this is a pretty powerful shortcut, and you can use this for computing expectation of more complex random variables. Right. So, there are several other properties of expectation, but I am not going to bother with those. These two, the two properties that I mentioned are perhaps the most important properties of expectation. So, let us go ahead with some examples. Let us take the simplest example, which is x is distributed as, let us say, a uniform is in the range of a to b. What do I mean by that? Well, fx of, by that I mean fx of x is equal to 1 by b minus a if x is in the range of a to b and 0 otherwise. You can easily see that this is a valid probability density function, because if you drew the density of if you could graph the density function, you would look like a rectangle, and the area of rectangle is exactly equal to 1 by b minus a into b minus a, which is 1, where we will assume that b is greater than a. Right. This is the density function of the uniform, this is the uniform distribution, right, uniform density function. What is the expected value of this random variable? Well, you have integral minus infinity to infinity, but for all purposes it is only a to b that matters, because outside a to b it is going to be equal to 0. Right. So, it is going to be integral a to b 1 by b minus a into x dx. X into fx of x dx. This is fx of x, this is x, this is dx, these are 3 terms. 1 by b minus a is a constant, you can take that out. X dx is simply x squared by 2 within the limit a to b, which is equal to half into b minus 1 by 2 into 1 by b minus a into b squared minus a squared. And what is that? Well, b squared minus a squared can be factorized as b plus a into b minus a, this is equal to b plus a by 2. This is not particularly surprising. If x is uniform in the range of a to b, expected value of x is clearly the average of the two endpoints. I mean, if you have a uniformly distributed rod between a and b, you can balance it exactly at the point a plus b by 2, which is the midpoint of a and b, which is not a surprising thing, but it is good to check, do a sanity check of our definitions. Let us do maybe a slightly more complicated example. Let us take x to be the right angle triangle example that we had. Fx of x is equal to, say, x by 2 if x belongs to 0 to 2, 0 otherwise. Right. So, this also we checked, this is, it is a valid density function. What is the expected value of this random variable? Once again, you do not need to integrate from minus infinity to infinity, you can just integrate from 0 to 2, integral 0 to 2 x into fx of x dx, x into x by 2 dx. So, this is going to be x squared by 2, this is half x cubed by 3 within the range 0 to 2. So, this is 1 by 2 into 8 by 3, so which is 4 by 3. Okay. So, what this says is the expected value of x is 4 by 3, and this kind of does make sense, because fx of x, x takes the values within the range of 0 to 2, but it is much more likely to take larger values than smaller values. Why is that? Because the density increases as you go from 0 to 2. The density is not constant between 0 to 2. If the density was constant between 0 to 2, the point at which you can balance the scale is exactly at the midpoint, but you have a triangular kind of plot where the density increases as you move from 0 to 2. So, x is you should immediately guess that Ex should be greater than 1, but obviously it should be less than 2 because the maximum value itself is 2. So, Ex is equal to 4 by 3 is the answer here. Okay. So, these are some examples. You can just use simple first principles to get the expected value of x from the density function if you happen to have the density function. Right. So, then we will move to the next object, which is the variance. The variance is also the same as we defined for discrete random variables. You can have a random variable, continuous random variable x. Variance of that random variable x is simply the expected value of the squared deviation of x from Ex. You can do a simplification as the same way that you did for discrete random variables. You would get that variance of x, expected value of x squared minus expected value of x the whole square. The intuitive meaning, we have seen this already in the case of discrete random variables. It essentially measures on average how much does x deviate from its expectation, right. So, this average, on average how much does x deviate from its expectation. So, there is a squared here to ensure that there is no negative numbers. You could argue, well, you can use absolute value as well, but the standard definition of variance is to use a squared deviation. The square root of the variance of a random variable is often called the standard deviation. Square root of variance of x is the standard deviation. This is another standard, this is the definition. Right. So, let us compute, let us do some simple examples, and okay, before we go there, let us see what are the properties of the variance of x. Let us do the properties. Unlike expectation, you do not have linearity of variance. You do not have that variance of x plus y in general is not equal to variance of x plus variance of y. There are of course special cases where it does happen. We will take a look at this later on, but in general you do not have variance of x plus y is equal to variance of x plus variance of y. And you do not even have well, you do have some property like this. Variance of a times x is equal to a squared times variance of x. Let us say a is some constant, let us say 2, right. If you have x, the variance of x is let us say 5, what is the variance of 2 times x? That is 4 times the variance of x, which is would be 20, right. So, that is an example. A is some constant, variance of ax, recall ax is also a random variable, right. So, you can imagine y as equal to ax, y is also a random variable, variance of y is simply equal to a squared times variance of x. You can guess why the a squared comes from, because you can essentially take a squared outside of this, and by linearity of expectation you can take a squared outside and you will get a squared times variance of x. This is pretty easy to prove, and this is also easy to check. It is easy to come up with a case where variance of x plus y is not equal to variance of x plus variance of y. The easiest example would be, let us say x is any non-zero variance random variable, y is equal to minus x. If you said y equal to minus x, variance of x plus y is equal to 0, right. Variance of 0, variance of a constant function is 0, but variance of x plus variance of y is not 0, because variance of x is non-zero, variance of y is also non-zero. And there is another trivial property, which is that variance is always positive or non-negative. It can be 0 also. Variance of x is greater than or equal to 0. Why is that? Well, that is because of the consequence of the squared thing, expected value of x minus Ex the whole square. So, this is the average of the random variable given by x minus Ex the whole square. If you take, let us say, if you define y to be equal to x minus Ex the whole square, y is a positive random variable. So, expectation of a positive random variable has to be positive, or at least it can't be negative. It can be 0 if the random variable happens to be 0. When is it 0? That is the next question. So, y, let us say if you say y equal to x minus Ex the whole square, the only time when the average of y is equal to 0 is if y is always equal to 0. So, when is y always equal to 0, that means that x is always equal to Ex. That effectively means that variance of x is equal to 0 only if and only if x is a constant, right. X is always equal to the same thing regardless of what outcome is. I mean you do have an experiment, let us say, let us take the height measurement experiment, right. But I can say x is equal to 3, right. If I say x equal to 3, then it does not matter what the height mean, the outcomes do depend on the experiment, but this particular random variable is a constant. So, the variance is 0, right. So, only constant random variables have variance to be equal to 0. So, let us do some simple examples. Let us take the example of uniform first. In fact, that is the only example we will do. Let us say x is distributed as uniform between a to b, right. We have already seen this, where fx of x is equal to 1 by b minus a within the range of a to b and 0 otherwise. What is the variance of x? Well, we will use the other definition of variance of x, which is expected value of x squared minus Ex the whole squared. We already know what Ex is, that is b plus a by 2. What is Ex squared? Let us do that. What is the expected value of x squared? Here you can use the function of random variable expectation rule that I mentioned earlier, that is, so you can use integral minus infinity to infinity, or rather a to b, integral a to b x squared into fx of x dx. What is fx of x dx? Within the range of a to b, it is simply 1 by b minus a. So, this is equal to 1 by b minus a into x cube by 3 within the range a to b, which is 1 by b minus a into b cube minus a cubed by 3. This is exactly equal to 1 by 3 into b squared plus a squared plus ab. So, this is expected value of x squared. But what is variance of x? Variance of x is simply expected value of x squared minus Ex the whole squared. Right. What is Ex squared? Ex the whole squared. Ex is b plus a by 2, Ex the whole squared is b plus a the whole squared by 4. So, you can take this term and subtract these two terms, right. 1 by subtract this term from this term, Ex squared minus Ex the whole squared, and you would get variance of x to be equal to b minus a the whole squared by 12. Right. So, this is simple algebra, you can do that and get variance of x is b minus a the whole squared by 12. And when is variance of x equal to 0? When b is equal to a, right. When b equal to a, variance of x equal to 0. And what does it mean to have b equal to a? Well, x always is going to take the value of a, which is equal to b, right. So, that is the only time when you have uniform random variables having a 0 variance. Okay. So, I have mentioned variance as a measure of spread of the random variable around the mean, and this also kind of captures that, right. So, for uniform random variables, b minus a is the measure of, is exactly equal to the spread of this random variable, and variance of x is simply b minus a the whole squared by 12 for this particular case. In general also this is true, that is variance of a random variable measures essentially the spread. How if you graph the density of density function of this, what is the width of the density function, right. How big a graph should you have for drawing this, that is given by the variance. Now we will move to another concept, which is conditional expectation. Right. We have already seen conditional density functions, and we can immediately guess what conditional expectations are. You can have, let us say x is a random variable, x is a random variable and a is an event, right. You can have expected value of x given a is simply equal to integral minus infinity to infinity x times conditional density function. The only difference from expectation is that instead of using the standard density function, you are going to use the conditional density function. That is the only difference. Okay. Conditional expectations are also a very powerful tool, and in machine learning in particular, conditional expectations are in fact one of the fundamental tools for building on top of on which regression, classification, everything is built. Let us see a simple example again for conditional expectation. We will go back to the example that I mentioned at the beginning. Let us say you have you are going to a bus stop uniformly between 7:10 to 7:30, and there is the bus arrives, there is a bus that which arrives every 15 minutes from 7, 7:15, 7:30 and so on. How would you compute the expected, let us say x is the amount of time that you are waiting for the bus. What is the expected amount of time that you are going to wait for the bus? Now you could compute the density function of this this random variable, that is the waiting time, and directly do it. But in this case, instead of computing directly the density function of x, it is actually easier to compute the density function given an event. Right? Let us it's the waiting for bus experiment. Let us now define x is the amount of waiting time, x is equal to waiting time. X is the waiting time. Let us define A to be the event that x is between R. Right. A is the event that you arrive at the bus stop, arrival at bus stop. Is earlier than 7:15. Right. So, A is the arrival. So, if you arrive, given that you have arrived earlier than 7:15, what is the density of x? Right. What is fx given A? You can by logic you can say given that you have arrived earlier than 7:15, you could have arrived any point between 7:10 to 7:15. So, you can say that this is uniform in the range of 7:10 to 7:15. So, uniformly between the total waiting time can be any time between 0 to 5 minutes. So, that is going to be equal to 1 by 5 if x belongs to 0 to 5, 0 otherwise. Fx given A of x is this. So, conditional expectation of x given A is also pretty easy to compute because this is exactly equal to uniform 0 to 5. So, which means that expected value of x given A is equal to 2.5. Okay, that is fine, and similarly you can do the same thing for A complement also, that is the interesting part here. A complement means that you have arrived at the bus stop later than 7:15, but you know for sure that you will arrive before 7:30. So, the total waiting time here would be uniformly between 15 and 0 to 15, right. You could have arrived exactly at 7:15 or you could have arrived exactly at 7:30, which would correspond to the extremes of 15-minute waiting time and 0-minute waiting time. So, Fx given A complement would be equal to 1 by 15 if x belongs to 0 to 15 and 0 otherwise. Fx given A complement of x is also easy to write. So, this is exactly uniform 0 to 15 and you can compute expected value of x given A complement also pretty easily, which is simply b plus A by 2, which is 7.5. Now, it is very easy to compute expected value of x and given A and expected value of x given A complement. These are very easy to compute, but that is not what we wanted. We want expected value of x, and here is where you can use what is called the total probability law, which is written as follows. Expected value of x is simply equal to expected value of x given A into probability of A plus expected value of x given A complement into probability of A complement. This is called the total probability law, and in this case to compute E of x we already have Ex given A and we also have Ex given A complement. Now we just need to compute probability of A and probability of A complement. What is probability of A? What is that is exactly equal to the probability that you arrive at the bus stop before 7:15, and we know that we know from our probability measure that you arrive uniformly between 7:10 and 7:30. So probability of A is exactly equal to 5 by 20, which is 1 by 4. So now we have Ex is simply equal to 1 by 4 into 2.5 plus 3 by 4 into 7.5. What is that? Well, 1 by 4 into 5 by 2 plus 3 by 4 into 5 by 2, which is 8 to 5 plus 45 is 50 by 8, which is slightly more than 6 minutes, which is 6.25 minutes. You could have computed fx, the density function of x directly, right. I am not saying it is impossible, but you can see that density function of x given A and density function of x given A complement is significantly easier to compute, and they happen to be nice uniform distributions. So which means that the expectation is also easy to write, and Ex becomes pretty easy to compute by using Ex given A complement and probability of A and probability of A complement. Right. So the total expectation is a pretty powerful tool for computing expectations, and especially in cases where you have a very easy nice split of outcomes. In this case you either catch the bus at 7:15 or 7:30, right. So there was a clear two possible groups of outcomes, and conditioning on each group makes life significantly easier. Right. Right. So with that we can wrap up this lecture.